Hello class, this is Dr. Viv. In this video, I'll start by solving a pretty simple Newton's second law problem, which is indicated here. I have a wedge that's fixed and two masses, m1 and m2, on smooth inclines of angle alpha and beta. My aim initially is to find the acceleration and the tension between the two strings, the common acceleration of the masses and the string tension. So the way we do this type of problem is to proceed by the usual methods of free body analysis. So for the mass m1, I'm going to create a free body diagram with respect to the reference frame indicated here. Let's just suppose that m1 is heavier in some fashion, so it makes the mass slide down there and pulls up m2 along this incline. By the way, it doesn't really matter if m1, if you assume that m1 has got this property or m2 has got the property to make the acceleration go that way. I'm just arbitrarily choosing a direction to solve the problem. So we can draw the various forces acting upon the mass m1 represented as a dot. That's the normal force, the force of gravity. And because there's no friction, there's just going to be one more force, and that is the tension force Ft. This angle is alpha, because that angle is 90 minus this angle is alpha, and this angle is going to be 90 minus alpha, so therefore this angle also is going to be alpha. We can draw exactly identical picture for the other incline, the gently sloping incline. Because it's accelerating this way, I'll take the x-axis to be along the direction of acceleration. That's always been my convention with drawing these free body diagrams. So now let's put the forces acting on m2. That's an equal and opposite force to that tension force there. Then you have the normal force Fn2, which is always perpendicular to the surface of contact, and then m2g. This angle is beta, therefore this angle is 90 minus beta, and therefore this angle is also beta. At this point, we are ready to fill up or populate our force tables. So let's do that next. I like to follow the same set procedure for every problem. There are three forces, and we're going to indicate their x and y components. Do the same thing here. Name of the force, the x component and the y component. Tension, normal force, gravity, here the tension is in the negative x direction, so that's the x and that's the y. The normal force is 0 in the x direction and F sub n1 in the y direction. Gravity is adjacent is cosine, opposite is sine, so that's going to be positive m1g sine alpha, negative m1g cosine alpha. Let's do the same thing over here. Tension here is positive. normal force. And then both components of gravity are in fact negative with respect to this coordinate system. So our force tables have been populated. Next, we write Newton's second law for these systems. For the system on incline alpha, I have sum of all the forces in the x direction, which is going to be negative ft plus m1g sine alpha. I'm going to write sine ss to save writing and time. And that's equal to mass times acceleration. The sum of all the forces in the y direction, well, we know from experience that there is no acceleration in the y direction. So I get Fn1 is simply equal to m1g cosine alpha. Cosine will be written as c. Let's write the same equations for incline beta next. I get f sub t minus m2g sine beta equals m2a, and then for the y direction I simply get the statement that the normal force is m2g cosine beta. So the equations look extremely symmetrical, as they should. Equations 1 and 2 have to be solved simultaneously to find our items of interest, which are a and f sub t. Now the easy thing to do is to find the acceleration. For this, I will put the equations one below the other. So equation 1 is going to be negative f sub t plus m1g sine alpha equals m1a, and equation 2 is f sub t minus m2g sine beta equals m2a. Adding two equations means adding the left hand side, putting the equal sign, and then adding the right hand side. If I add the left hand sides, you'll notice that the tension terms cancels. So I just get m1 sine alpha minus m2 sine beta times g on the left side. On the right side, I get m1 plus m2 times a. So that solves for me the acceleration. It's just m1 sine alpha minus m2 sine beta divided by m1 plus m2 times g. Let's put a box around it because that's a significant result. It's one of the results we were asked to find. Now, one way to find the tension is to substitute the value of the acceleration in one of the equations, 1 or 2, and solve. I never like doing that because that's too much work. Besides, you'll never get a cute expression. So what I will do is continue playing with equations 1 and 2. What I'm going to try to do now is to eliminate. In the first method, I eliminated tension and got the acceleration. Now I'll strive to eliminate acceleration. To do this, I'll multiply the equation 1 by m2. Let's see what I get. So I'm going to get by negative m2. So I'm going to get m2 times ft minus m1 m2 g sine alpha is equal to negative m1 m2a. And then I'll multiply equation 2 by positive m1. That's equation 2. So I'm going to get m1 f sub t minus m1 m2 g sine beta is equal to m1 m2a. Now you'll notice that when I add these two equations, so the operation here is adding the two equations, I'll indicate that with a plus with circle around it. The right hand side will be 0. The left hand side is just m1 plus m2 times f sub t minus all of this stuff, and that's m1 m2 sine alpha plus sine beta times g, which immediately gives me the tension with absolutely no fuss at all. That's f sub t. F sub t equals m1 m2 over m1 plus m2, our old friend, the reduced mass, shows up. In the previous video I introduced this term, mu reduced. It shows up in every two-body problem involving Newton's laws. Sine alpha plus sine beta times g. So we have solved the entire problem. But the title of this video was not 2 blocks on an incline solve. It was Stevenius's perpetuum mobile proof. So what is that? It's a very, very famous proof by the Dutch engineer and physicist Stevenius. Around his time, people were trying to make machines that constantly produce energy with no other means. So machines that give unlimited energy are called perpetual motion machines. Today we know for various reasons that they don't exist, but a good deal of time and capital was spent, actually even today, by some misguided people. You'll find these people still working on this in their workshops. So the perpetual motion machine of Stevenius's time was this one. Let's suppose you had a really smooth incline that's fixed with angles alpha and beta, and you had a really heavy necklace that's put around that wedge. Now because this is so steep, it's going to pull this wedge, this portion of the chain up, and this thing is going to keep rotating forever, producing unlimited energy. So this was the perpetual motion machine idea, and people built it, and they tried running it, and they found that it soon stopped. Now we'll prove that that's always going to happen. There's going to be no acceleration. Now it might so happen that if they make it really smooth, then it'll have a constant velocity and go around. That's allowed. But the acceleration will be 0. Let's prove that. For the acceleration to be 0, I can use my condition a equals 0 from the equations we just developed. And that gives me m1 sine alpha is equal to m2 sine beta. Now, for a chain of this uniform construction, we can assume that the mass is proportional to length. So I'm going to write m1 is going to be some proportionality constant, I'll call lambda, times L1, where this length of the incline is L1 and that incline length is L2. And the mass m2 then is going to be lambda times L2. Now I'm going to put that in my condition for acceleration to be 0, and that gives me lambda times L1 sine alpha equals lambda times L2 sine beta. The lambda term cancels. It's just a proportionality constant, and I get L1 sine alpha is equal to L2 sine beta. But L1 sine alpha is just a height. Height equals height, and that's obviously true in this case. So in this particular case, because L1 sine alpha is the same as L2 sine beta, multiplying it by lambda, you're going to get this condition, and that's precisely the condition for 0 acceleration. So there's going to be no acceleration, and therefore it does not begin moving. That's very important. These choice of words is very important. It doesn't begin moving. But if it's already been set in motion, will it ever stop? In a very ideal world with no air resistance and no energy loss to vibration and any of those things, no, it'll keep moving. Such a perpetual motion machine which keeps moving but does no useful work is called a gift motion machine. So the best that you can have from a machine like this is a gift. But of course, in the real world, that never happens. Air resistance and vibrations will eventually slow down even a constant velocity Stevenius perpetual motion machine.